Hello, everyone. Dr. White back again for the third in our series of screencasts on open intro statistics, sections 3 and 4 of chapter 1. Last time we talked about confounding variables, which can often arise in observational studies. And we showed an example of a hypothetical observational study about cars and their color and whether or not they get a ticket, where there was clearly a possible confounding variable that could keep you from inferring that the color of a car helps to cause whether or not you get a ticket, even though car color might very well be associated with whether or not one gets a ticket. I had claimed towards the end of that screencast that experiments are not as likely to be plagued by confounding factors as observational studies are. So I want to back that up here, but do it by talking a lot more about experiments and how they're designed. And you can see that when we design them, we're looking for like all the ways we can to kick out these confounding factors and to make experiments the kind of study where it's going to be easier to infer causation once you've found an association between two variables. So I remind you of the definition of an experiment that we gave in the first screencast of this series. In an experiment, you still maybe have two variables in mind, an explanatory variable and a response variable. But you're not just gathering some subjects and recording the values of both those variables. No, no, no. In an experiment, the researcher is assigning the values of the explanatory variable to the subjects. And then, without any interference at all, recording the response variable for each subject. Just by the way, there's some terminology you will meet in, this book and in your statistics life in the future. The people that are in the experiment, they're called subjects. They're also called experimental units. They don't really have to be people. They could be, like each subject could be a plant in some biology experiment. There's lots of different types of things that could be the subjects in an experiment. The explanatory variable in an experiment is often some kind of categorical variable with a few possible values. And it often gets called a factor. Doesn't have to be, but often you'll see in books and research articles the explanatory variable in an experiment is called a factor. And the possible values of the explanatory variable are called its levels. And since the researchers are assigning subjects to, or since the researchers are assigning the value of the explanatory variable to the subjects, then they're actually putting the subjects into groups where everybody in a group has the same value for the explanatory variable. And those groups get called treatment groups. Okay, so there's going to be as many treatment groups as there are possible values for the explanatory variable in an experiment. Now, observational studies are subject to confounding variables because the groups in the study can be different from each other in a way that is relevant to the response variable, but is not just the difference in the explanatory variable. So think about the example of the car color and whether or not you get a ticket. You got your bright colored cars and your drab colored cars, your two groups. And they're different in that way. But unfortunately, they're also different in what kind of drivers they have. The bright colored cars tended to have your more aggressive and fast drivers because aggressive and fast drivers like the color. And the drab colored cars had the conservative drivers. And so this aggressive versus conservative driver difference between the two groups of cars. That's a difference other than the explanatory variable, but it's relevant to whether the car gets a ticket. And it's something that you can't, just sort of kick out of that study. And so people who want to do experiments, they think about that and they think, how can we assign assign values of the explanatory variable to subjects so that that doesn't happen, so that the different groups, the different treatment groups, are as similar as possible with respect to every variable that might affect the response variable, except, of course, the explanatory variable itself, where they differ in that. If you could get this to happen, if you could get your treatment groups to just be the same looking, except for how they're treated, then if they differ in their response variable, you can attribute that difference to how they're treated and not to some other variable out there. Then you could really say, yeah, it's the X variable that's causing the Y. It's how we treated them that made the difference. So here we are trying to, assign people into their treatment groups, assign values for the explanatory variable to all these subjects. And you might wonder, well, how can we do this so that they really do look the same? You might imagine that you could just let the researchers kind of like take each subject and decide for themselves, look at the subject and say, well, you should go here. Now this other subject should go into this other treatment group because this other subject kind of looks similar to this subject over here, and we want to make the groups look similar, so let's put you in this other group. You can imagine letting the researchers just use their own judgment like that. But actually, we don't do that because researchers often have a vested interest in how the experiment is going to come out. And we want people to be able to trust the results of the experiment. And so we want the researchers to be actually separated from this process of assigning subjects to the treatment groups. And so actually, in a well-designed experiment, the researchers will, to some extent at least, use chance to assign subjects to groups. Like it could be as blind as something like a coin flip to decide whether a subject goes into one group or the other group. In fact, in what we call a completely randomized design, which is the main experimental design that we're going to talk about in this course, the subjects are divided into the available treatment groups solely by chance. There are other ways of designing an experiment where you use stuff other than chance, but you bring those stuff in a way so that it's never just left up to the judgment of an individual researcher who goes where. But we're going to stick with the completely randomized designs where it's just like totally matter of chance. And so that means, let's say, if you've got a treatment group that is supposed to have M people in it, then every set of M subjects out of all the subjects that have volunteered to be in the experiment has got to have the same chance to be that treatment group. So like if you had like 400 people that volunteered to be in an experiment and you had 4 treatment groups and you were going to have 100 in each group, then say for that first treatment group, going to have 100 people in it, every set of 100 people out of these 400 people, every set, there's a lot of sets of size 100 when you got 400 people, has got to have the same chance to be that first treatment group. And every set of 100 has to be have the same chance to be the second group. And every set of 100 has to have the same chance to be the third treatment group, and so on for the last one. When that happens, when you're doing this completely randomized design, then if you've got a lot of subjects, then the treatment groups are also going to be pretty large. And there's math probability theory that comes in and says, if the treatment groups, the larger the treatment groups are in a randomized design, the more likely it is that they're going to be similar, except, of course, in the value of the explanatory variable, the treatment group they're in. Just to give you an idea of how this might work, if you could somehow make an experiment out of that car study, where instead of just taking the drivers with their cars and then getting them, to drive down the road, what if you divided them into two groups by a coin flipping process? And group one, so like every driver that comes up, you take them in their car and you flip a coin. And if it's heads, you paint their car yellow. And if it's tails, you paint their car gray. Okay. Then think about what happens if you have a lot of people in the experiment. Well, every time a really aggressive, fast driver comes up, you flip that coin. 50% chance that aggressive driver is going to be driving a yellow car, and 50% chance they'll be driving a gray car. So say if you had 1,000 subjects, you'd expect about if you had 1,000 aggressive drivers, you'd expect about 500 of those aggressive drivers to be stuck in yellow cars and about 500 to be stuck in gray cars. And how about conservative drivers? Say you also had 1,000 conservative drivers volunteering for the experiment. Then about half would be, again, in each group, the yellow group and the gray group. And so then when you look at the end at your yellow cars and your gray cars, the drivers of them are going to be the same on the whole. I guess there's a tiny chance that a whole bunch of the aggressive drivers just happen to, say, get into the yellow group. And a whole bunch of the conservative drivers get into the gray group just by chance. It's just like if you flip a coin 1,000 times, I guess just by chance it's possible that it could have 900 heads. But those chances are really, really small. So that's the beauty of a completely randomized design. If you've got a lot of subjects in the experiment, chances are your treatment groups are going to look pretty similar in terms of the subjects that are in them, except, of course, in the actual treatment group they're in, the value of the explanatory variable. Here's another example, just to get you thinking more about it. Suppose you're interested in seeing whether taking aspirin reduces the risk of heart disease. And let's suppose that 200 people have agreed to participate. So the explanatory variable here is going to be whether or not a person takes aspirin. That's going to be your factor. And the possible values of it are going to be takes aspirin, does not take aspirin. So like you're going to divide the people into two groups. And in one group, the people in that group are going to have to take aspirin every day for some period of time. And the other group, people will not take aspirin for some period of time. So those are the two levels, the two possible values of the explanatory variable. And if you do this completely randomized design, then you're going to end up with the two treatment groups that could have 100 subjects in each group. Like maybe you can design, I want the two groups to be the same size. That's often a nice idea if you can arrange it. And so the aspirin group, you can plan for it to have 100 subjects, and the non-aspirin group, you can plan for it to have 100 subjects as well, out of the 200 who have volunteered to be in the experiment. All you got to do is just like pick randomly out of your 200 people, pick 100 of them to be in the aspirin group. And then the remaining 100, just throw them into the non-aspirin group. By the way, the non-aspirin group here, that's often called in experiment world the placebo group. We'll see why that term is used very soon. But another term that could be used is control group, because they're not getting the special, the special little treatment, the aspirin. So when you set up an experiment, good idea to use a completely randomized design to get the subjects into their treatment groups. But there's some other things that you can do to ensure that the two groups are going to be the same except for how they're treated. And this involves blinding. If possible, a researcher is going to try to keep the subjects in the experiment from knowing which treatment group they're in. Because sometimes when you know what group you're in, when you know how you're being treated, that can affect your behaviors or your attitudes in a way that may have an effect on the value of the response variable for you. So this is called the placebo effect. So for example, people who think, that they are getting some special new revolutionary treatment for a disease, even when they're not, because they think they may be getting that treatment, their attitudes may be better, their stress levels may be lower, and it's possible that that kind of thing, that kind of mind-body interaction, can have some effect on how well you actually do with the disease that the experiment is trying to measure. So it would be nice if nobody, the people getting the treatment, like the aspirin in this experiment, and the people not getting it, the people who are not taking the aspirin, it'd be nice if they just didn't know whether they were taking aspirin or not. So you might wonder, like, how is that? How can that be arranged? Well, it's arranged through the use of what we call a placebo. So the aspirin group, they all take aspirin each morning for some long period of time. But the non-aspirin group takes an inert substance that comes in jars that look like aspirin jars, and little pills that look like aspirin pills and taste like aspirin, and so on. But it's some inert substance that's known not to do anything to the body. And so then both sets of subjects are on the same footing. They both truly don't know whether they're taking aspirin or not. Everybody is like, well, there's a 50-50 chance that I'm taking aspirin. And so there's no difference in their mental attitudes, no difference from any stress levels resulting from different mental attitudes, and so on. No chance for a placebo effect. So the terminology is strange here, but when you introduce a placebo into an experiment, it takes away the placebo effect. Another really good idea is blinding the evaluators. So, the researchers in an experiment, some will have different jobs than others, and it will fall to some of the researchers to measure the response variable. Like maybe there will be doctors who make the decision about whether a person has had a heart attack during that period of time. And, whether or not you have a heart attack, that's a judgment call. It requires some professional knowledge. The doctor has to think about it, look at your symptoms. And if the doctors have some vested interest in the outcome of the experiment, like if they'll get famous for discovering that aspirin can reduce the chance of heart disease, then it's possible that maybe subconsciously they could tend to, if they know that a person that they're evaluating was an aspirin taker, then they might tend to think, oh, well, that wasn't really a heart attack. It was actually this other thing, and to kind of make things look good for the aspirin group. And you don't want that to happen. And so you don't want the evaluators who are measuring the response variable to know which group a subject is in. So that's another kind of blinding. So you can blind the subjects. You can also blind the evaluators in some experiments. Now, you can't do this all the time. Like if you could somehow make an experiment out of the cars situation, you can't blind the subjects. I mean, the drivers are going to know what color car they're in. You can't blind the evaluators because, well, it might be difficult. Maybe you could somehow give traffic information to the people who are counting up who got tickets without telling them what color the car is. That might be tough, though. But in many situations, particularly in these kind of drug studies and medical treatment studies, it often is possible to blind the subjects and blind the evaluators. And if you are doing both, then you've got what's called a double-blinded experiment. And that's a randomized double-blind experiment is kind of the gold standard for making your treatment groups as similar as possible in every way, except in how they're treated. And that makes it easiest to infer that the explanatory variable causes the response variable if your data analysis finds they're associated. I'm not saying that observational studies are useless. There are some things that you can do if you can collect enough data of the right sort. You can do what's called correcting for confounding factors, and that can make observational studies partially useful for inferring causation from an association. But it's a tougher, harder road to hoe, and that's why we really like to do experiments if we are able to do them. If we have the money, the resources, and if it's ethical to do them. So next time, we'll look at another example, this time of a real-life experiment that really happened here at Georgetown College. And we'll actually analyze it right out to the end, really trying to do inference about causation. So we'll see you then.